Hi. Observing the graph of a function, apart from the decreasing-increasing behavior, we may notice another qualitative property. That is that in certain sections, the graph appears to be curved upwards or downwards. Upwards, like in the green sections here, or downward, like in the red section here. Now, while this observation is intuitive, it is clear that terms like upwards or downwards do not seem very professional. So, how can we formalize these properties? Let's try to understand it. To do this, we start with a function that is curved entirely upwards, resembling then to a parabola, which is the orange function we have here. Here we may notice the following remarkable property. If we fix any 2 points AFA and BFB along the graph of the function, the segment joining these 2 points, which is represented in green here, lies above the graph of the function, which is the orange line. Let's formalize this property. Now, if we pick a point x between a and b, the quote on the function is f of x, while along the straight line joining these 2 points is this value, f of a plus fb minus fa divided b minus a times x minus a. So, if a function f is given on an interval I, and it is such that the quote f of x is less or equal than the quote along the segment, which is this quantity, this for every x between a and b, so between the initial and the final point, and moreover, whatever are these 2 points a, b taken in interval I, then we say that the function f is convex. Convex functions are usually introduced using an equivalent formulation that it's a little bit much easier to write, which can be obtained as follows. Let's rewrite this property, and I call it here FA and FB because I want to emphasize the right-hand side in terms of these 2 quantities. So let's regroup the expression at the right-hand side. We see that the coefficient of f of a is b minus x divided b minus a, plus something times f of b, and this coefficient is now x minus a divided b minus a. Now here we may notice that if we call lambda this number is between 0 and 1, because x ranges between a and b, so when x is a, this is 1, when x is b, this is 0, and it is decreasing with x, and this one is exactly 1 minus lambda, so again it varies between 0 and 1. Moreover, if lambda is this quantity, we can easily see that x is lambda a plus 1 minus lambda b. Therefore, this inequality can be also written in this form. F of lambda a plus 1 minus lambda b must be less or equal than lambda fa plus 1 minus lambda fb, whatever is lambda between 0 and 1, and whatever are a and b in the interval I. That's the usual definition, the most popular definition of a convex function. In the definition we gave, we did not impose any differentiability or continuity condition on the function f. Actually, we plot the figure of a very smooth function, but that's not needed. In fact, an interesting remark is the following result, that if you have a function f which is convex on an interval, then necessarily this function must be continuous. So we cannot plot exactly any function to have convexity, but necessarily it is a continuous function. We can have an example of continuous function which is convex but not differentiable. The modulus is such example. It is a function which is clearly convex but not differentiable at some point. Now, let's see why this result holds. To do this, let's take a point x. Let's fix x in the interval and take a strictly less, which will be fixed, than x, and b strictly greater than a. So a and b are fixed in the interval strictly less and strictly greater than b. So they make basically a neighborhood of x. We take a y here at right of point x. And we write the convexity of the function saying that the blue segment, which is the segment joining the xfx to bfb, is above the graph of the function. So in particular, the function f at point y will be less than the quote along this blue line, which is f of x plus fb minus fx divided b minus x. This is the angular coefficient times y minus x. Let's save this inequality for future use. And now we do a similar argument by using the convexity property for the segment that joins AFA to YFY. So now the point is x, which is between the initial and final point, so f of x will be less or equal than the corresponding quote on this green segment that you can easily see. It is f of a plus the angular coefficient, which is now f of y minus f of a divided y minus a times x minus a. Now we want to use this second formulation to isolate f of y. So we rewrite this saying that it is f of x less or equal than f of y, which is multiplied by x minus a divided y minus a, plus f of a, which is multiplied by this coefficient, y minus x divided y minus a. Now, since we took x between a and b, in particular x minus a is different from 0, we can divide by this factor here, which is non-zero. So we multiply by the reciprocal of this, so which is y minus a divided x minus a. And what we obtain by doing this is f of x times y minus a divided x minus a is less or equal. Now we have f of y alone plus f of a, and this is what we get. F of a times y minus x divided x minus a. Finally, carrying this at left, we have this final inequality, f of y larger than this. Now, you remind that we had initially found a bound, upper bound for f of y. So let's take out this bound from the freezer. And so we have the lower bound, which is the bound we have just found, and the previous bound, the upper bound. So this says that f of y is between these two quantities. Now it's time to return to the goal. The goal was to show that function f is continuous at point x. So we have to take the limit of f of y when y goes to x. Here, since in this game y is larger than x, we are doing the right limit. So what happens when y goes to x from the right? Look at the left-hand side here. This is constant f of x. Y minus a goes to x minus a, that divided by x minus a makes 1, so this part here goes to f of x, minus f of a times this, but now y minus x goes to 0, so this factor goes to 0 and this goes to 0. So in particular, the left-hand side here will go to f of x. Similarly, when y goes to x, this is constant, it remains f of x. This is another constant, it does not contain y, while this last term goes to 0. And therefore, also the right-hand side goes to f of x. Then we can apply the squeeze theorem to conclude that also f of y, which is in the middle of the two, will go to f of x. This means that we prove that the right limit at x of f is f of x. So f is continuous from the right at point x. Similarly, you can prove that f is continuous from the left, and I warmly suggest you to fill out the details, reworking what we have seen. Basically, you have to put now the point y at left and do the similar argument. So it's a nice exercise for you. One of the beautiful aspects of convexity is its rich geometric interpretation. For example, if now f is differentiable on the interval I, we notice that if f is convex, then the graph of the function lies above now each of its tangents. This can be formalized. If f is defined on I interval, it is differentiable on I, we can prove that f is convex if and only if this property holds. So we want to say that f lies above each of the tangents. Let's fix a point A where we take the tangent. So we will write f of x greater than the tangent at point A, which is f of a plus f prime a times x minus a. Now this property must be verified for every x in the interval I, and for every a, so whatever is the point where we take the tangent. So for every x and a in I. Now, to prove that this is equivalent to convexity, in this case, it's a very good exercise for you. This characterization of convexity has an important implication for optimization problems. Let's observe the graph of a function, a convex function, for which there exists a point where the tangent is horizontal, so a stationary point. The derivative of f at that point equals 0. Then, because of convexity, the function lies above each of the tangents, so in particular it will be above that tangent, f of x star plus f prime x star times x minus x star. But since at x star the derivative is 0, this means that f of x is greater or equal than fx star for every x in I. And this tells that if we have a differentiable and convex function on an interval I, and x star is a stationary point for the function, then automatically that point x star is a minimum for the function f on the interval I. So this is very important because it says that in this particular case, the first order condition identifies the minimum point, which is a very nice result. Another intuitive observation is the following. Suppose that the function f is convex and differentiable on some interval I. We may notice that as we move the variable x from left to right, the tangent line tends to rotate counterclockwise. Geometrically, this means that the slope of the tangent increases. So we have the following result. If f is differentiable on the interval I, f is convex if and only if the derivative of f is increasing on I. Now, since we know how to verify that the function is increasing, we just compute its derivative and we check whether it is positive or negative. We immediately have the following corollary. So here we have to apply this fact to the function f prime. So the derivative of f prime is what we call the second derivative of f. So suppose that f has a second derivative. We say also that it is twice differentiable on interval I. Then the function f turns out to be convex if and only if the second derivative of f is positive on the interval I. Great! I hope this video was helpful to you. I have given you various ideas for work, such as finding the proofs of the different properties we have presented in this video. Here is another task to try. Observing the slopes of the chords drawn from a fixed point A to a moving point X at the right of A, you will notice that the slope of the chord increases. In mathematical terms, these are the slopes. This is an increasing function of x. So your task is to prove this just by using the initial definition of convex function. Another fact is that the definition of concave function is when the concavity is pointing downward. So we say that f is concave when minus f is convex. So a good thing to do is to review all the results we have seen for convex function and to see what they imply for concave function. Good job.